Hey, what's up guys? Jeremy here from RoboDK. Welcome back to this second webinar. I'm super happy to be here again. You guys were more than 200 for the first live broadcast, and if I count everyone that watched the replay, nearly 1,000 people saw the first webinar within only 3 weeks. Of course, we hoped for good results, but this is clearly more than what we expected. So some of you guys even personally contacted me via email or LinkedIn to share your thoughts and constructive comments. So simply wow. I'll speak for the whole team here by simply saying thank you. That being said, you guys are here for more cool insights about RoboDK, so let's jump to today's topic, mechanisms. Mechanisms can be many things inside RoboDK. That includes obviously the robots and the standard external axis, linear rails and turntables, but it can pretty much be anything, any positioner or gantry. It can be a conveyor, it can be a stamping machine, a sliding door, some two-finger grippers, and so on. So let's look at the agenda for today. We will start simple, just so that you all know how to properly set up a station with a linear rail. Then we will see how to manipulate that kind of station. They require some specific attention here and there. Nothing too complicated, but still. Once you have a good grasp of the basics, we will create our own custom linear rail and our own gripper, like the one you see right now. And for the next example, we will be a bit more creative in our usage of the mechanisms. Why not simulating a conveyor or a CNC door? So you will soon realize that custom mechanisms have way more potential than it appears at first in terms of creating a more realistic robotic station. It can even be very useful for those for offline programming. It can help you take into account any moving parts, like a clamp, for example, in the collision detection process. So we will then continue with the rotative axis. We will create a custom one as a positioner, just like that. And for those who follow our YouTube channel, this was part of a tutorial video I did for our Autodesk Inventor plugin. In that tutorial, I voluntarily avoided talking about the positioner, so we will cover that today. And after that, we will explore the first steps towards a robotic station using 7, 8, or even 9 axes for offline programming. This is often used for tasks such as welding or milling. Don't forget that you guys can ask questions at any time in the chat, either publicly or privately. Some members of RoboDK are also connected to the chat and will be happy to answer the quick ones, and I'll answer what's left at the end of the presentation. That's a pretty stacked agenda, so let's get started. Okay, for the first example, we will start with an empty station. The goal here is really just for you to better understand how mechanisms work and how to manage the relationship between, let's say, a linear rail and the robot on top of it. So let's simply open the online library. In the filter here, let's go for external axis. You can find a few external axes that were already created for in the online library, but you can obviously create some custom afterwards. I'll show you that later on. So you have turntable and positioner, and you have linear rails for different supplier. So I will simply import the standard 3.5 meter linear rail from ABB. So download. I can reset the filter here and close that for the moment. So here we have our linear rail. First thing to take a look at is that it was imported with a reference frame, exactly in the same way as when you import a new robot. It comes with its own reference frame as a base. Here I will simply call that frame rail to make things a bit less confusing for you guys, and this will be the rail. So I'll call that linear rail, and here frame linear rail. Okay, cool. If I double click the mechanism here or double click the mechanism, the linear rail itself in the station, I will have a linear rail panel, pretty much the same thing as when you open the robot panel. And you have a slider here because you only have one joint instead of 6 with a standard 6-axis robot. That moves the platform, or the platform on top of the rail itself. One important thing to notice is that the movement is always along the x-axis here. So this is something to keep in mind when you will create your own linear rail. I'll show you that later on. This one can go from 0 millimeter to 3.5 meters, so 3,500 millimeters. So this is the range that you have here with this one. Here the reference frame that you see on top will be very useful. This is where you will import the robot or anything that you put on top of the linear rail. So this will be the origin of the 0, 0, 0 of everything that will be attached to the linear rail. Talking about that, let's import a robot. So I'll open the online library. I'll simply pick an ABB IRB 2400, and here it is. So I'll just take the time to rename that. My goal is really to be as clear as possible for you guys, so I'll just take the time to change that. So we have the frame of the robot, which is the base, and the robot itself. So now I can simply drag and drop that on top of the linear rail, and everything that is a children of the linear rail will move with the linear rail. So if I move it here, you can see that it's moving together. Right now you're asking yourself, like, why this didn't import itself directly at the root of this, at the origin of this reference frame here. This is simply because the reference frame of the robot itself had a 1000 millimeters offset along Y. And I will also take the time here to rotate this, so this is pointing towards us. Perfect. This way it makes sense. Okay, so now, like I said before, if I move the linear rail, everything moves with it. I'll simply add a tool here, add a TCP, simple dummy TCP, just tool. And I don't need to see the robot flange anymore. So now I have a tool here to create small programs and targets, stuff like that. So talking about targets and programs, let's start with the first one. So I'll create 2 targets that are attached to the frame robot right here. So first target and then second target here. So they are reachable obviously this way. And considering that they are part of frame robot, which is also part of the linear rail, if I move the linear rail, both targets follow the base of the robot. So I can select them, right click, create program, and now I have a simple program that reach 2 points, and no matter where I place this, it will work. Perfect. Now if I delete those and I create myself a reference frame outside, which is not an independent reference frame, which is not linked with the linear rail itself, I can again create targets in this one. So the first target, and let's say the second target. And if I activate this reference frame, I can go target 1 and target 2, and I can create my program here. So this way. But now, considering that those are independent, if I move independent from the linear rail, if I move the linear rail, you can see that those 2 targets stayed in place. And if I try to run prog1, it tells me that move J to target 2 is not reachable. I have to go to bring back the linear rail to an acceptable position here for it to be able to reach this point here. Many position can be acceptable. This doesn't need to be the exact same position as I had when I taught those targets, but still. Okay, so this was the first few informations I had to give you before going further with mechanisms and robots. So let's jump to the other example. In this example, we are showcasing a UR robot mounted on a custom linear rail from Vention and using a 2-finger gripper from Shunk, simply carrying a wrench from for a tray to another tray. So fairly simple in terms of task, but a lot of cool information to get from this demo. So we will have like 2 phases of this example. The first one will be, in the first one we will learn how to create the program, the position in the program to manage the movement of the linear rail and the gripper. And in the second phase of the example, we will learn how to create those custom mechanisms. So let's stop this one and jump to this other station here, which is pretty much the same thing as the other station, except that I removed a lot of objects, targets and stuff like that, just to make things a bit simpler so it's easier for you guys to follow. So here I already have the target to pick the wrench, and I already have the target to place the wrench in the second tray. And I already have like folders created. So we have pick programs where I can pick range at the first position, and in the place folder I can go and click place range pos 2. But again, as I explained in the first little demo, considering that the linear rail didn't move, the target 2 is not reachable in this case. So I'll click OK, and I would need to like move the linear rail around somewhere around here and relaunch this program for it to work properly. I can replace object to bring back the wrench. Okay, so first I will have to create 2 positions for the rail. So one around 1800 millimeters and one around 150 millimeters, something like that. Those positions should be placed in the linear rail parent reference frame. This is where I recommend you to place it. It just makes more sense to do this this way. So let's create one. Okay. First thing to know is that by default, RoboDK will create targets in programs that are linked to the main robot of the station. So it's more common to create targets for the robot. So by default, it's normal to create those linked to the robot. So if I right click the target here and I go robot linked, you can see now it's the UR5E. But I can simply click on linear rail to link this target to the linear rail itself. So this is the first thing to do. Next thing, let's go and just rename it pos 1, rail pos 1 and rail pos 2 here. Second things that I'll recommend you is to convert the Cartesian target to a joint target. So the goal is simply to, so the big pro of doing that is that you won't have to manage the reference frame nor the tool that will be linked to that target. You can simply call a move J with this joint position, and it will work automatically. So I can hide it because I don't need to see it. We can still know that it's a joint target considering the little green dot just right here. And now I need to go to 150 here, and I'll right click and click teach current position. So now no matter where I place the linear rail, if I click here, it will be back at 150 millimeters. I can Control C and then Control V this one, F2, and then to here. I'll bring that to 1800 and then right click teach current position, position 1, and then position 2. Perfect. Now let's create the programs that are linked, that we can call to move the robot. So those are just targets, positions in fact, so we cannot like call them in a program. We need to create the program. So let's create a program, call it rel pause 1, and let's go take rel pause 1 and simply create a linear movement. So already we have something a bit weird that occurred on screen. So we know that the yellow line is there to display the path. But why would the path do that strange move if in fact it's supposed to move along the linear rel? And if I run this program, the robot does a very strange movement to reach that point. I'll bring that back to home. Oops. Yeah, home. Perfect. This is, again, for the same reason as when we linked the target to the linear rel. The programs, when they are created, are linked with the main robot. So now we can simply click here and click linear rel. And this way, the yellow line will be along the rel, which makes more sense. And we can move to pause 1. I don't need to set the frame, and I don't need to have the TCP, as it's just a joint target that I'm using. Okay, now I can Control-C that and then Control-V to have the other one. Let's go pause 2, and then I simply need to re-affect or relink the right position. So rel pause 2 and then rel pause 1, and I don't need to see the path every single time. I'll select both of those programs and I'll bring them in the rel positions folder. So I really like using folders. It keeps things a bit more organized, especially when you start having like 20, 50 different small sub-programs. It can get a bit messy. So folders are a very good idea. Right-click the station and add folders to add another folder. Okay, now let's do the same for the gripper. So if I double click the gripper again, I can move from between 0, which is completely closed, up to 40 millimeters, which is completely open. In our case, we'll have to go between 10 and for the pick position and 40 for the fully opened position. Again, I will create those targets right in the chunk gripper base reference frame. So let's create a first target. So if we remember well, right click, linked, robot linked, chunk gripper, F2, gripper, pause, pick. I forgot a capital P. And transform that into a joint target. And then we are at 10 right now, so I can right click and say teach current position. I can Control-C that and then Control-V. F2 here to transform that into open. So we have gripper pause, pick and gripper pause open. This one needs to be at 40 millimeters, so I can just change that here. Right click and teach current position. So here, pick, open, pick, open. Again, I don't need to see those, so I can render those invisible. And I can simply now create the programs to open and close the gripper. So new program, F2, gripper, pause, pick. We already know that we need to relink with the gripper. And now I can pause pick and then move J. Don't need this. It's gonna pick and then Control-C and then Control-V. This one is pause open. And then here, pause open, boom. Again, I'm gonna select those, bring them in the gripper position folder. So this way I can simply close that if needed. And they are already called in the pick. Here call gripper pause pick, and then here call gripper pause open. Obviously those stations are already available on the web, so I'll give you the link afterwards, so you can like check that out more in details afterwards. Now I want to create my main program, so I can select in the right order the subprogram I want to run. So holding control. So rel pause 1, I'm gonna pick range pause 1, range I'm gonna go rel pause 2, and I'm gonna place place range pause 1, and right click and make main program. As you can see, they are in the order I selected them. I don't need to see the path, and I can simply run this like that. Perfect, super simple. Okay, now that this is done, it's time to jump to the creation of those linear rails and two finger grippers. So to do that, I will recommend you to do those steps in an empty station, simply to avoid confusion with the other objects that you already have in your station. It's just like a cool way to keep things simple. So I just press Control and N to create a new station. I will create myself a reference frame that will just call frame linear rail. Okay, like that. And here in another folder, I have the linear rail, the linear axis rail, and the linear axis mounting. So like the mounting on top of the linear rail. So if I bring them one after the other, so the rail here, I could have bring both at once. That would have also worked perfectly. So here I have the rail and the mounting here on top. Perfect. So the next thing to do is to create the rail itself. So here, if we remember well, I told you before that the movement will be along the x-axis. So the rail at the moment is properly placed. If it was not the case, I could simply like modify the position of the rail with respect to the linear rail here. But it will the movement will be with respect to the x-axis of the linear rail. So the rail itself won't move, but the tray on top will move along the x-axis. So to create, I'm gonna scroll back a bit. To create the linear rail, you click on Utilities and then Model, Mechanism, and Robot. And this little wizard, if I can say, will appear. So you can give a name to your mechanism. So this is the first thing. So this is gonna be linear rail. You can create many mechanisms from this window here. So one rotative axis, two rotative axis, linear rail, T-bot, linear and rotative, two finger grippers, and so on and so forth. You can even create your own SCARA robot and 6-axis industrial robot right here. So yeah, okay, back to the linear rail. By default, it selected the only reference frame that we had in our station. This is one of the reasons why I prefer doing that in a new station. It's just like easier. There's less possible confusion. And it selected the linear rail, the first object as the base, so as the part that is not moving, and the second object as the part that is moving. I could invert those if it was not properly set up. Okay. Now I will click here on update. I know that my settings are not fine, but this is just to show you guys what happened. First, big recommendation, do not click on OK up until the point that you are sure that the settings you entered there are the settings that you want to use, or in fact that makes sense for you. So here in the rod panel, you can see that I have a slider that can go between -200 and 200. So here, if I move here, you can see the mounting plate moving. As you can see, it's not. Oh, here I have a small. Oops. Okay. Here, as you can see, it's duplicated the object that we had. So the point here is simply to not overwrite them, simply to keep them. So if we need them afterwards, they'll still be available here, like that. And here we can manage the joint limits. So here we do not need to go under 0. In fact, so 0 will be our limit. And here the maximum will be 2100 millimeters. So now if I click update, automatically the mechanism is updated, and I can move from one side of the linear rail to the other fairly easily. So to create a linear rail, it's pretty much that as simple as that. If, for example, you don't really know why, but the linear rail does not go in the proper direction, so the movement is not in the proper direction, you can simply click on invert here, click update, and then it will move the other way. But for us, this is perfect. Okay, so this is how you create a linear rail. Afterwards, I would simply select that, Control C, and then bring that to my the station I want to work in. Okay, let's go for the 2-finger gripper. So Control N again to create a new station. I will again create a new reference frame. So frame 2, call it frame gripper, and here in another folder, in the same folder, sorry, I have the gripper and both fingers. So I can simply drag and drop that here on the reference frame. And now I go utilities and model, mechanisms, and robot. So here it's going to be a 2-finger gripper, and I'll call this one gripper. Okay, perfect. Here, on purpose, I mixed those a bit so that I can show you that you can reposition them. So first I need to have chunk gripper, small, here, F2, chunk, perfect. So chunk gripper, and then finger 1, and then finger 2. This one will go from 0 to 40 millimeters. I know that according to the data sheet of the gripper itself, so I didn't I picked that out of my head. It's really just the real value. Now if I update this, I don't need to see the tool frame, the reference frame, or road fringe. I have movement, I have my 40 millimeters movement, but instead of going towards the middle when I'm towards closing, it's disassembling itself along the way, which is not what we are looking for, obviously. So there's 2 ways to fix that. The first one would be to, I'll just delete this. The first one will be to have this gripper here in its closed position, so in the 0 position before starting the creation of the mechanism. So here -40, and then I'm going to utilities, model, mechanisms, and robot, 2-finger gripper, and then gripper, finger 1, finger 2, 0, and then 40, and update. That should work. Now it open, 0 to 40 open. So this is the first way of fixing that situation. Another one would be to, I'll just go back to the original situation here. And by the way, this also works for linear rails or turntables and others, so this is not only for grippers. The other options that we have, because right now if we go and update that, now I should have the same problems that I had before, yes. Okay. The other way of fixing that is telling RoboDK what was the value of the joint when it was at this exact position, so when you imported the gripper. So in this situation here, it's already at 40 millimeters, so I can, here in built joints, I can already enter 40 millimeters and click update. and it should work. Yeah, it's working right here. You can also change the home value. So let's say here you want home to be at 40 instead of 0. Update. So now every time you'll press home, it will go back to its fully opened position. Okay, so that's it for this example. Let's jump to the next one. So here's the next example. In this one, I'll start it. We are simply doing some machine tending applications, so feeding a CNC lathe with a Omron TM robot and a dual handy gripper from RoboDK. So in this one, I used mechanisms in a more creative way, if I can say. So as you may have already seen, the door is animated, so I pretty much simply created a linear rail or linear axis where I put the door, and there's like 2 positions to reach, so either opened or closed here. And the double handy is like really 2 gripper that I created and placed at a 90-degree angle. I'll show you how I did that later on. And here we have the conveyor, which take the parts and bring them out of the station. I won't talk about the input conveyor, so this one is a bit different, and this is more for advanced user. So if you're one of those, you can always take a look at the API folder that is here. I have a few macros in there that will help you create exactly the same station as that. So if we go here for the simple handy, so this one is pretty simple. It's exactly the same thing as I did before for the shank gripper. So simply a 2-finger gripper that I created as a mechanism. And then afterwards, I placed 2 of those on the mounting on a mount with a 90-degree angle here. So now I can control both in a independent way. So both are specific mechanisms. Yeah. One thing that I forgot to say before, and I'll go back to my example here, and I'll bring that, yeah, I'll rotate this so it faces us. Even if I'm creating mechanisms, I always create TCP. I'm just gonna make them visible, TCP here and TCP there, minus a few times. So the mechanisms here are part of the robot, so they are attached at the flange of the robot, but I'm also creating TCP, so right click and add TCP, so that I can attach parts to those TCP. So this is very important to do also. And here, pretty simple for the lathe itself. The CNC lathe, it's the casing was the base of the linear rail, and the door was the moving part. So I can either open it completely or close it completely. I created 2 positions, so completely open or completely closed, and I'm calling this subprogram depending of the needs. Yeah. And last but not least, the conveyor. So you can find a conveyor like this one directly in our online library. So if you go here and in the filter, you go to object, oops, you have here conveyor belt mechanism. This one, Python simulation, is a bit more complicated. So if you can stick to this one, I'll recommend it. And it will create exactly this conveyor here. So this conveyor, when open, is pretty much just a linear rail of 500,000 millimeters, in which I created a F3, a target, oops, stop, a target at the end of the rail, so at 500 millimeters. So what I'm doing here, I'm calling a program called conveyor run, which slowly bring the linear rail to its final position, which is 500,000 millimeters. And as soon as you can see right now, I'm going to bring that back to 0. Here you can see that the reference frame conveyor here, which is attached to conveyor belt, is moving. And anything that will be part of this reference frame will be moving also. So if I bring that back to 0, this side here part will be change support conveyor. And now if I run conveyor, the object follows. So and if I had more than one object, all of those will follow. If the speed of the conveyor is not like the right one for my needs, I can always go in parameter and then change the speed and acceleration right there. By the way, you can do that with all the mechanisms you're creating, so it's important. By default, it's like 1,000 millimeter per second and 5,000 degrees per second, so it's very fast. Yeah, you can need to change that. Okay, next example. For the third example, here we have a project that I already used in the past in one of my tutorials. So it was a tutorial with our plugin for Inventor. So if you go on YouTube, on our YouTube channel, by the way, we have a lot of super interesting tutorials, and you can even have access to the replays of RoboDK webinar. So like exactly like the one that we are doing right now, the replay should be online somewhere this afternoon. Here for the plugin, Inventor plugin, I created this station where I'm kind of deburring a car rim. So if I just like start the deburring program, so pretty much just following the edge of the part. And here I placed that on a turntable. So far we only like worked with linear rail and two-finger gripper. So now let's talk about turntable or positioner, in fact. So in this case, the same pattern, the same deburring pattern repeats itself 6 times around the rim. So no need to create 6 times the same pattern or the same path for the robot. I can simply create once the path once and then rotate the rim 6 times. So this is exactly what I did. So here, if you go in turntable position, you can see that there's position 1, position 2, position 3, position 4. By double clicking, you are going directly, so you won't see it rotate. So if I go 1, 2, 3, 4, 5, and then 6. And to actually execute the program, the only thing I did in my main was calling like here I have the program to just call like the turntable to move at the right position. And here what I'm doing is like call turntable table position 1, then call the rim program, then call table position 2, call the rim program, and so on and so forth. So this way, and I'm following the path and then rotating. So this is how to use a turntable as a positioner. So there is no synchronization here between the robot and the turntable itself. We'll talk about that like in a moment with the next example. So here, yeah, like position 4, and then we're doing the same pattern over again. So it's pretty simple, but pretty effective instead of having to create the same program over and over again. Obviously, this program is a real program that you can export. So if I would just right click the program here and generate robot program. So this is a Kawasaki robot. And here I would have all the moves and positions to reach to be able to actually do that path here. So this turntable or positioner, in fact, was something that I created myself. It's not something that you can buy or use. In fact, it's just like a 3D model that I created. And if you want to create that turntable, we will again Control N, create a new station. Again, here in, I'll create first my reference frame, turntable, And then here in a folder, I have both parts that I need to import. So turntable, the base, and the rotative power part. So I'll just like import the base and import the top right here. Now that this is done, again, utilities, model, mechanisms, and robot. And here we have rotative axis, which is the first options you have, the first option you have. Again, we'll call this one turntable. And here the base reference frame is turntable. I should have called that turntable frame. Let's do that real quick. Frame turntable, which makes more sense. Here it's updated. And here you can say, okay, this is 0, and this, let's say it can do 2 turns. So 720 degrees, and let's update that. Now, if I use the slider here, you can see the top of the turntable moving around. For the rest, it's when you want to create the program, it's exactly the same thing as when we were creating program for the linear rail. There's actually no difference in between. Okay, up to the next example. So for this last example here, we have a way more advanced project. So this one use a linear rail and turntable, but 2-axis turntable and a robot. So this is a real project we're working on right now with a research lab near Montreal. So our goal is to test some milling performance with or without our calibration package. So we are really excited about that. And I will create a webinar especially on this subject as soon as we have the result. So that should come in maybe 3 or 4 webinars, something like that. But here I just want to show you what you can achieve if you want to use RoboDK for the offline programming feature. So if you really want to output a program from RoboDK using external access. So here the big difference, I created 2 programs, so they are it's exactly the same path for both. But one is using the turntable only as a positioner, so to position the part in a place, in a position where the robot can work on it. And the other one is using both the robot and the turntable at the same time. So here if I run the no turntable, so you can see that it's keeping, I'm just gonna use the slider here, it's keeping the part at the same position, so it's simply positioning the part in a certain way, and then it lets the robot do the entire job, in fact. So here, but here if I go with turntable, so this time both the turntable and the robot are used, so they are working together in a synchronized way to achieve the path. So in this case here, the synchronization was not really necessary because the path was acceptable or achievable simply with the positioner, but it's not always the case. When you're doing machining, when you're doing welding or other like tasks like this, sometimes you really need both to work together or move at the same time in a synchronous way to avoid things like singularities, joint limits, or reach limits in general. So here, so I'm just in this webinar here, I won't go too far with that. I'm just going to show you what are the basics you need to understand. So here you need to create your station exactly like we did priorly for the other example using linear rails. So the rail with the robot attached on top of it. And then here at the same level as the rail, we have the turntable here. So once you have this, you can right click the robot and then synchronize external axis. In here, you'll be able to select which axis is synchronized with the robot. So once this is done, when you open the robot panel, instead of having only 6 joints, you'll now have 9 joints, or depending on how many external axes you synchronized. And so all those are working together now, and they are all part of the same kinematic assembly. So, and once this is done, the only difference I have here in my machining programs between the one with no turntable and the one with a turntable, so I shouldn't call that no turntable, it's more like turntable as a positioner, and then here turntable synchronized, is the fact that here I didn't check the turntable optimization for the turntable as a positioner, and I did click the optimization turntable for the one where the turntable is used in a synchronous way with the robot. So yeah, really important to mention is that this is not necessarily supported by all robot brands. This is your job, guys, to do your due diligence and make sure that before engaging yourself in such a project, that the robot or the equipment you are selecting are compatible. So obviously the big 4 are able to handle that, and other brands are able to handle that too, but it's not the case for every brand. So to give you an idea here, with the example I showed you in the last webinar, I've used for the sake of like simplifying the example, I've used the Doosan robot with the linear rail in a synchronized approach. But as far as I know, and I could be wrong here, correct me if I'm wrong, as far as I know, Doosan robots, collaborative robots, do not support linear axis synchronization. So this was kind of a stretch, if I can say. If you're just using that for simulation purposes, it's okay. It doesn't matter much. It makes simulation smoother, if I would say. But it's not exportable in real life because this robot do not support such feature. Yeah, so the real difference is like, instead of having to like bring the linear rail at a certain point and then go get the box, let's say, I can click once and both the linear rail and the robot will move to reach the position in a synchronized way. Okay, so that's pretty much it for this last example. Perfect. Okay, that's pretty much everything for today's webinar. If you think it was helpful, please hit that like button and subscribe to our channel. We will release more of those in the future. You really don't want to miss any of this. And remember, if you have any technical questions, you can reach us via the forum, so www.robodk.com/forum. We'll be happy to help you with your project. Have a great day.